For this example, we will use m equals 13 and a equals 7. We will start with r1 equals 1. r2 equals 1 times 7 mod 13, which equals 7 mod 13. Since 7 is less than 13, this equals 7. r3 equals 7 times 7 mod 13, which is 49 mod 13. To work out 49 mod 13, we need to determine the highest multiple of 13 that is less than 49 and subtract it. 13 times 3 is 39, and 49 minus 39 equals 10. So R3 equals 10. R4 equals 10 times 7, that's 70, minus 13 times 5, that's 65, which equals 5. R5 equals 5 times 7, minus 13 times 2, which equals 9. R6 equals 9 times 7, minus 13 times 4, that is 11. R7 equals 11 times 7, minus 13 times 5, which equals 12. R8 equals 12 times 7, minus 13 times 6, which equals 6. R9 equals 6 times 7, minus 13 times 3, that gives us 3. R10 equals 3 times 7, minus 13 times 1, which equals 8. R11 equals 8 times 7, minus 13 times 4, which equals 4. R12 equals 4 times 7, minus 13 times 2, which equals 2. And finally, R13 equals 2 times 7, minus 13 times 1, which equals 1, which brings us back to the start. The good thing is that we have a full cycle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. However, the big problem with this method is serial correlation. When points are chosen in n-dimensional space, it results in all of the points lying on at most m to the power of 1 on n parallel hyperplanes. What does this mean in terms of the data so far? Let's plot the random numbers in 2 dimensions. To do this, we will take each sequential pair of points and plot them. The first point will be R1, R2, which is 1, 7. The next point will be R2, R3, which is 7, 10. Then 10, 5, 5, 9, 9, 11, 11, 12, 12, 6, 6, 3, 3, 8, 8, 4, 4, 2, and 2, 1. Now let's plot all of these points in 2 dimensions. We'll start by plotting 1, 7, which goes here. Now we plot 7, 10, 10, 5, 5, 9, 9, 11, 11, 12. Can you see a pattern emerging? 12, 6, 6, 3, 3, 8, 8, 4, 4, 2, and 2, 1. Serial correlation results in all of these points falling on these 2 lines. The problem is that we are not exploring all of the sample space. We are only testing these 2 small regions. What we want is to have our random numbers spread around evenly, like this. See how these numbers are spread everywhere? While there are large areas here that are not tested. So the linear congruential generator is useful to see how pseudo-random numbers are generated, but in practice we would use a better algorithm, such as the Monte twister.